All right, 23, we have 2 high schools that have a similar number of students and parking lots, a similar size. The safety officers at both schools want to investigate whether there's an average difference in number of cars parked per day in the student parking lots for the school year. A random sample of 15 school days will be selected. For each selected day, the number of cars parked in the student parking lots will be counted at both schools and a difference will be recorded. Assuming all conditions for the inference method are met, which of the following is the appropriate test for the investigation? Okay, so it looks like we're collecting, we're comparing means. So sample means, we're going to compare. And we're picking a random sample of 15 days. But for each day, you have two data points: the number of cars parked at one school and another school. So you have a matched pair. Each day you have a pair of cars that you're using to calculate the difference. So let me kind of like do an idea. Let me do an example. Like let's say let's pick like parking lot A, parking lot B, and then you have like, data point 1 for each. But then you're recording the differences. Like let's say x1 minus y1 or something like that. So each of these are pairs. Each day, like you could say day, day 1, day 2, day 3. You collect for each day. For the 15 days, you're counting the number of cars at each parking lot, then comparing the differences. But these are the matched pairs. So then it would be C. I feel like I made that seem a lot more confusing than it was. I don't know. Sometimes I know my students sometimes need a visual because they think of matched pairs like it always has to be people. No, it doesn't always have to be people. It just has to be two similar, individuals, but it doesn't have to be people per se. It could be like, cars, whatever, animals. All right, moving on. 24. The histogram shows the distribution of heights in inches of 100 adult men. Based on the histogram, which is the closest to the interquartile range in inches of the distribution. Remember the interquartile range, so from the 25th percentile to the 75th percentile. So since there's 100 adult men, we want to find where the 25th man would be, because that'll be the first 25% or Q1. So Q1 would be at the 25th guy. So let's just count. 1, 2, 4, 5, 6, 9, 13, 18, 24. So then the 24th, so up to here, that's the 24th. So 25 to the 25th guy lies in here somewhere. Q1 would be in there somewhere. Then let's look at the 75th person, or let's count backwards. So going from here, 25 back, 1, 2, 4, 6, 9, 14, 20, and 28. So here's the 20th. So the 20 to 28th lies in here. So then the 20 to so then the Q3 lies in there somewhere. So going from this interval to this interval, somewhere in like around 66 to 71. So that's about a distance of 5. And so the answer will be B. And just so you know, you can't find the exact answer per se, like, and that's not what they're gonna, and they don't expect that. So they won't have answers that are very close. They really just want to see if you get this general idea. So just make sure you understand that, that percentile idea when you were talking about interquartile range and Q1, Q2, Q3, and Q4 and all that. Number 25. A state study on labor reported that 1/3 of full-time teachers in the state also work part-time at another job. The average number of hours worked per week at the part-time job was 13. After an increase in teachers' salaries, well, I would like to get that. A random sample of 400 teachers who worked part-time at another job was selected. The average number of hours worked per week at the part-time job for the teachers in the sample was 12.5, with standard deviation 6.5 hours. Is there convincing statistical evidence that at the level of alpha equals 0.05, that the average number of hours worked per week at part-time jobs decreased after the salary increase? Okay, so we're basically going to do a significance test comparing means. So we have data here, like we have our original mean, the original sample, or like not original sample, but the original study had a mean of 13, and when they took a sample of, so in the next study, a sample of 400, and found a sample mean of 12.5 and a sample standard deviation of 6.5. So again, become very comfortable with your calculator. You can actually just run a significance test in here. Go to stat, go to stat, test, and all we simply need to do is a t-test, because it's just one sample a year. And that figure out, and we're gonna highlight statistics. I just did it, so it's already filled in. But you're gonna fill in your null hypothesis mean, or your population mean, be 13, because you want to test against that to see if the sample mean has strong enough evidence to say it could also be 13, or I mean, in this case, we want to find if there's significant evidence that the mean decreased. So the sample mean was 12.5, sample standard deviation of 6.5, sample size 400N, and our test highlights less than, because again, we're looking at decreased. Our null hypothesis will be that mu is 13. The alternative will be that mu is less than 13. And let's go to calculate, and it'll tell us it. We get a p-value of 0.06. So we don't have statistically significant evidence to say that it decreased because our p-value is greater than an alpha level of 0.05. So we would fail to reject the null hypothesis. And the answer would simply, it looks like it's just going to be the first one, it'll be A, because the p-value is greater than 0.05. So we fail to reject the null hypothesis. All right, so that's it for that one. Hope that helps.
All right, problem 26, we have at a state Department of Transportation study traffic congestion on a certain highway, and to encourage carpooling, the department will recommend a carpool lane if the average number of people in passenger cars on the highway is less than 2, and the probability distribution of the number of people in passenger cars on the highway is shown in the table. Based on this distribution, what's the mean number of people and passenger cars on the highway? Okay, so this is basically an example of a random variable. So we want to essentially find the mean or the expected value of this random variable, which is called x. And that's essentially the weighted average of each of the individual x values. So remember, these are their possible values for x. 1, 2, 3, 4, 5. And what this equation says that you take that value and you multiply it by its corresponding probability. You sum all of them up. 1 times 0.6 plus 2 times 0.28 plus 3 times 0.0 8 plus 4 times 0.06 plus 5 times 0.02. And let's just do the start calculator to do the work. We get 0.56 plus 2 times 0.28 plus 3 times 0.08 plus 4 times 0.06 plus 5 times 0.02. I just realized I wasn't typing multiplying. So it's 3 times 0.08 here. Parentheses, plus 4 times 0.06 plus 5 times 0.02. All right, so should get 1.7. And this will give us answer C. Now you don't have to memorize this formula. Remember in your formula sheet, there's all these formulas that you can use. So what we're looking at here is this. This is the expected value of X. But make sure you understand this notation. This sigma symbol means sum them up, the probability of each corresponding X value. To compare the effectiveness of two treatments, researchers conducted a well-designed experiment using a randomized block design in which subjects were blocked by age group under 40 years and 40 years or older. Which the following must be true about the randomized block design of the experiment. Okay, so remember what a block design is. It's essentially like the same concept of a stratified sample, except in regards to experiments. So you basically break the subjects into groups of similar individuals according to some variable, like according to some characteristic. Maybe so again, see, like maybe the maybe it was, well, you know, like it's probably age had a significant factor on the effectiveness of these treatments. So they wanted to block for age. They grouped them based on their age, under 40 and over 40. Well, let's just go through these. So here we got the number of subjects in each block is different. Now it says must be true. It doesn't have to be true. This could happen sometimes, just based on just the number of people you get in the study. But this doesn't have to be true. It's actually better if they were the same. So it's not going to be A. B, treatments are randomly assigned to subjects within each block. Yeah, so this is what you want. So essentially you have your subjects broken into like block A, so let's say under 40, over 40. And then from here, you split the under 40 group according to the treatment but you randomly assign them. So maybe they get let's say treatment 1. Let's say T1, and these subjects could get treatment 2. And you do that same sort of thing for the other block. You randomly assign treatment 1 to some of the subjects and treatment 2 to the other subjects. So within each block, you're going to have random assignments. Let me just briefly talk about the other ones. The design cannot have a control group because subjects are blocked by age group. That's not necessarily true. They can still have a control group. Remember, it's saying must be true. The experiment uses a matched pair design where subjects from one block are paired with subjects from the other block. No, it's not. No, because they're blocked by age group. You have the 40-year-olds, or you have the under 40 separated for the over 40, so they're not going to be paired up with each other. And yeah, so it's not going to be E. It's not going to be that this group is not just going to receive one treatment and the other group won't. Is not going to just receive the other treatment. Again, within each block, you're going to make sure that each group gets randomly assigned treatments. So the answer is definitely B. 28, probability. All right, die used in a certain board game has 8 faces, of which three are red, 3 are yellow, and 2 are blue. Each face is equally likely to land face up when the die is tossed. In the game, a player tosses the die until blue lands face up, and the number of tosses before blue lands face up is counted. For example, a player who tosses the sequence shown in the following table has tossed the die 3 times before the blue lands face up. So we want to find the probability that the player will toss a die at least 2 times before blue lands face up. So we want to find the probability that you're going to have a color other than blue on your first toss, the probability of either getting a yellow or red. This is toss 1. And if you need to get this 2 times, you're gonna multiply this by again getting a yellow or a red. So you're gonna multiply by the probability of getting yellow or red, because these are independent. Now, it doesn't matter what you got on the first toss. Remember, this is toss 1, this is toss 2. So as long as you get yellow or red on both tosses in a row, you're still going to be rolling die. Now, what's the probability of getting a yellow or red? Just think of it as one toss at a time. So there's there's 3 red and 3 yellow out of 8. So there's out of 8 possibilities, 6 of them are either yellow or red. So this is 6/8. And same thing, since again the die, it's not if they're independent, you can still roll the same thing again. So it's just 6/8 times 6/8. So 36 over 64. And then the decimal approximation, it's probably going to be a little more than that, I'm guessing. Yeah, 0.5625. So the answer will be D. All right, 29, we have a statistical test that involves the following null and alternative hypotheses. We have that HO is that mu is 64, and that HA, the alternative hypothesis, is that mu is greater than 64. So which of the following describes the type 2 error? So let's remember what the type 2 error is. That's when we fail to reject the null hypothesis, fail to reject HO, when the alternative, so when HA is true. Failing to reject the null hypothesis when the alternative is true. So the null hypothesis is that the mean is 64, and the alternative is that it's more than 64. So that means that we basically believe that the mean is 64 when it's actually greater. So let's see which of those would make sense. So failing to reject the null hypothesis when a population mean is 64. No, it wouldn't be A. It would be when it's greater than 64. So it looks like it's going to be B. Failing to reject HO, the null hypothesis, when the population mean is greater than 64. And so yeah, that would be B. Population mean being greater than 64 is HA. The answer is simply B. All right, 30. The marketing director for an ice cream company investigated whether there was a difference in preference for 2 new ice cream flavors, cotton candy and mango. Each participant from a large group of people was randomly assigned to taste one of the 2 flavors. After tasting, each person rated the flavor on a numerical scale from 1 to 5, where 1 represented strongly dislike and 5 represented strongly like. 2 sample T interval for a difference between 2 means, cotton candy minus mango, was constructed. Based on the interval, there was convincing statistical evidence of a difference in population mean flavor ratings. Mango having the greater sample mean rating. Which of the following could be the constructed interval? Okay, this is a lot of wording, and the key is to construct it into like the proper difference of means. So we have, okay, we got a two-sample t-interval for difference of means, cotton candy, we're going to call that mu sub c, minus the mean of mango, so mu sub n. Let's construct it. But based on the interval, there is convincing statistical evidence of a difference in population mean flavor ratings, with mango having the greater sample meaning. Okay, so what this is saying is that the sample mean ratings, like that. So we're saying, so this is saying that the mean of mango, so mu sub m, is greater than the mean of the cotton candy. So mu sub m is greater than mu sub c. So if this is going to be what we're trying to figure out, let's look at this. Let's read this a little more carefully. If we're looking at an inference test, what the null hypothesis, or there being no difference, is saying that these two are equal to each other. So their difference would be equal to 0. But if we're trying to find the confidence interval where we have that the mean of mango was greater than the mean of cotton candy, then let's just adjust this by bringing the mean of mango onto the other side. So this is the same as this. But now, I actually didn't need to write that much. But if we're looking at that, we're saying that the mean of mango has a greater sample mean rating. Then this is basically saying that if we took mango away from if we took the mango, if we subtracted the mean of mango from each side, you would have 0 is greater than mu sub c minus mu sub n. So what does that mean? This is a negative number, because for this to make this is, I probably should have wrote it like this. So another way of looking at this is mu sub c minus mu sub n is less than 0. But we want to see which of these would have a negative value, would be censored at a negative value. Because in order for this to be true, we're saying that it has to be less than 0, or it has to be a negative number. So since they can only be scaled from 1 to 5, we would roll out A. That's too extreme. They're just going to go that far. B makes sense because it's centered on a negative value. And C wouldn't make sense because in here we have some positive values. We have to have only negative numbers. Only negative numbers will work for this. So this could be the only one that would give us reasonable evidence. Or sorry, B would be the only one that would give us reasonable evidence, because all the values in here are negative. All the values are here are negative. So the key in this problem is figuring out if we're going to look at a negative or positive. I think I made that sound more complicated than it should have. So I apologize about that. But just the answer is B, because it's all negative, centered on negative. All right, let's move on to third. The director of the marketing department wants to estimate the proportion of people who purchase a certain product online. The director originally planned to obtain a random sample of 2,500 people who purchased the product. However, because of budget concerns, the sample size will be reduced to 1,500 people. Which of the following describes the effect of reducing the number of people in the sample? Okay, so let's look at an expression that involves the sample size and proportion. And it looks like all these are we're talking about the variance. So remember, the variance is just the standard deviation squared. This is the standard deviation. So this is the variance. The variance is the standard deviation squared. We'll talk about sample proportion. So if we look at our formula sheets, in case you don't have it memorized, you do not have to have it. Look at the equation for standard deviation, which we have as this. So if this is standard deviation, when you square this, or square this, if you want to be more technical, it doesn't really matter. The square root would go away. So this would just be equal to p hat times 1 minus p hat over n. Right? And so you want to see what would happen when we change n from 2500 to 1500. What happens to this value? So in one case, we would have, let's say we would have this being equal to p hat times 1 minus p hat over 2500 versus p hat times 1 minus p hat over 1500. So what happens to this value? What happens when you divide from 2500 to 1500? Is this value going to be bigger or is it going to be smaller? That's what you want to essentially recognize. And since you're dividing by a lesser amount, you're going to have a bigger number. That's just simple math. And you can just test this with anything. 1 over 2500 versus 1 over 1500. This will be a bigger value. So since this is greater than that, that means the variance increases. The variance of not the population. This population, this is a sample, remember? Not B and not sample exactly, because technically we're looking at a sampling distribution. Remember, each sample size has its own distribution. The variance of the sampling distribution will increase. This is gonna deal with the stuff you cover in like a probability unit, probably chapter 7. But if you look in here, see how we're talking about parameters with sample distribution. Okay, so maybe that could help you. The answer would be C. All right, so from a random sample of 1,005 adults in the US, it was found that 32% own an e-reader, which the following is the appropriate 90% confidence interval. Estimate the proportion of all adults in the US who own an e-reader. Okay, so we always start off with our point estimate, which would be p hat. So they all have, 0.32 as p hat. Plus minus our critical value, in this case will be z star, times their standard deviation of the statistic, or standard error of the sample statistic. So using the formula, in case you don't have to memorize, no problem. We would just use this in this place. So the square root of p hat times 1 minus p hat. Okay, so p hat is 0.32 plus minus our z star. Remember, that's the critical value in the standard normal curve, where there's 90% of the area in the middle, or 5% on each side. So you can either use your z table, or table A, and find the z score where there's 5% to the left. But in this case, you would look from the inside out. So you want to be on here, somewhere in here. 0.05. So like about here, so it'll be something like negative 1.664, negative 1.645, negative 1.64, 1.64. We, it doesn't matter because we're adding or subtracting it. So let's just put 1.64 here. All right, I'll give it away. 1.645. It looks like they're using. So right now we know it's either going to be B or E, and the p hat 0.32. 1 minus 0.32 is 0.68 over 1005. That's your sample size. So the answer will be D. In B, they're trying to scare you with that, or trick you with that square root there. Careful about that. All for it now. All right, 33. Measuring the heights of a tree is usually more difficult than measuring the diameter of the tree. Therefore, many researchers use regression models to predict the height of a tree from its diameter, measured at 4 feet 6 inches from the ground. The following computer output shows the results of the linear regression based on the heights in feet and the diameters in inches recorded from 31 felled trees. Which of these will be 95% confidence interval for the slope of the population regression line? Okay, so we're looking for the slope of the population regression line. So remember, we have some depending on the form of the textbook, may have, y equals alpha, alpha times alpha x plus beta or something. Or it's essentially just slope intercept form, y equals ax plus b. But we're trying to estimate a, the true value of the slope from our sample. So we're given data already. So we're trying to find the slope of the population regression line. So let's pay attention to what we're trying to estimate from what. What's our explanatory versus our response? We're trying to predict height. So height is our y from diameter. And so then what we start off with, let's make the whoops. Get that backwards. Shows the based on heights. What's based on height? Sorry. That's flip-flop. And it's saying which shows the results based on height, so that means that height would be like the x. And then the diameter would be the y. So we're predicting, so flip-flopping the diameters from the heights. So our estimate, this will be our point estimate. We'll start at 1.054 plus minus. And remember, we have a 95% confidence interval. So we're going to use T star in this case. Because we're looking for, we're going to be looking at like the means. We'll be studying like the mean. We're not looking at proportion. We're looking at like the mean value to have an estimate. So we'll have a T interval, so our T star will be a critical value, times the standard error. So again, let's flip to our form, our packet, so easier, much more easier to recognize what's going on. And again, this is the general form of a confidence interval. So going from that, we need to find the T star value for a 95% confidence interval. And the sample size is 31. So n is 31. But in this type of estimation, we have to account for the degrees of freedom, and the degrees of freedom would be n minus 2, or in this case, 29. So we have to look for the 95% confidence interval corresponding to 29 degrees of freedom. So let's bust out our table. We're going to go to table B for this. So 29 degrees of freedom, 95% confidence. Lines us up with this value right here. 2.045. The visual again. Our T star is 2.045. And now we just use that and multiply it by what we have here, by our 0.322. That's our standard error. So overall, we're going to have the form, let me write it up here. So 1.054 plus minus 2.045 times 0.322. 1.054 plus 2.045 times 0.322. And with one side, you have 1.71. And we already can see that it's going to be B, but let's just verify the other side. So let's subtract that from 1.054 minus 2.054 times 0.322. And we get the other side, 0.396. Sorry for the messy handwriting. I usually write better. Angle here. Anyways, the answer is definitely. And 34. We got a group of 80 people who have been diagnosed as pre-diabetic because of high blood glucose levels. Volunteers participate in a study to investigate the use of cinnamon to reduce blood glucose to a normal level. Of the 80 people, 40 were randomly assigned to take a cinnamon tablet each day, and the other 40 were assigned to take a placebo each day. People did not know which tablet they were taking, and their blood glucose levels. All right, problem 34. We have a group of 80 people who have been diagnosed as pre-diabetic because of high blood glucose levels. They volunteered to participate in a study designed to investigate the use of cinnamon to reduce blood glucose to a normal level. Of the 80 people, 40 were randomly assigned to take a cinnamon tablet each day, and the other 40 were assigned to take placebo each day. The people did not know which tablet they were taking, and their blood glucose levels were measured at the end of 1 month. The results show that 14 people in the cinnamon group and 10 people in the placebo group had normal blood glucose levels. For people similar to those in the study, the data provided convincing statistical evidence that the proportion who would be classified as normal after 1 month of taking cinnamon is greater than the proportion who would be classified as normal after 1 month of not taking cinnamon. All right, so these problems are getting longer and longer. You gotta be a good reader and be patient. But all we're essentially doing here is we're gonna run an inference test. And the cool thing is that you can do this all in your calculator. So what we're looking at is we're comparing the two samples, and you want to see, are you comparing means or proportions? And it looks like we have 40 in each group, and proportion, we have 14 out of 40 and versus 10 out of 40. And we're going to go to, in your calculator, you go to stat, tests, and you go two prop d-test. And I read this earlier, but here it is. So X1, that represents the number of successes in one of the groups. But for 14, size of sample 1, 40. And X2, the number of successes in the second group, 10. Sample size 2, 40. And we're looking to see if the cinnamon group proportion is more than the one that didn't take, anything, the placebo. So since I made because I mean group 1 be the group taking the cinnamon, I'm going to have that P1 would be greater than P2. Depending on which way you did it, if you made group 2 be the cinnamon group, it would be the other way around. We're looking at P1 is greater than P2, and we can just calculate this. Bang! We get all of our information that we need. The key value here is our P value. That P value, not proportion, but our P value is 0.16 value. 0.1645. But this is not going to give us significant evidence at any real alpha level, because usually we'll have alpha levels, but at default it's usually 5%. Sometimes in business it can be as high as 10%, but this is way too high. So the answer would be E, because there's not convincing statistical evidence of any reasonable significance level. That's our alpha. All right. $35. A students working on a physics project investigate the relationship between the speed and the height of roller coasters. The student collected data on the maximum speed in miles per hour and the maximum height in feet. A random sample of 21 coasters with the intent of testing the slope of the linear relationship, keyword, between max speed and max height. Based on the residual plot shown, the conditions for such a test might not be met. Okay, so which of these conditions appear to have been violated? So there's 5 conditions you got to check. An acronym you can remember is minor. Want to check if it's linear, independence condition, the normal, approximately normal, equal standard deviations, and the residuals. So let's see what we got here. Not residuals, not residuals, sorry. Okay, so let's see which ones are. So random is met, it says right here. Linear is met, it says already there. And because there's random scatter, there's no obvious pattern in the residual plot. That's met. Independent. You can basically just based on the context, there's not going to be really there's like the results of one roller coaster is not going to affect, the speed of the other one. So that could be met. Normal now, and equal standard deviation. Now the normal one, as long as you see that, so there's another way of saying this, expected value. You want to look to see if it's spread essentially like it's centered at 0. And they're usually never going to make it that hard to verify. So this is, obviously centered at 0. Now this stands for equal standard deviation, or we're talking about how much the values vary. And let me actually draw a vertical line. And remember, the residuals are the distance from this center line to the point. And when this condition for it to be met, we want to basically believe that it's reasonable to say that all these segments are about the same length. But you can see they're not. It looks like they're increasing, or they're pretty different. We can't really reasonably say there's an equal amount of spread among the regression line. Because you go all the way to 0 to like nearly 40, and these ones are less than 5. Looks like less than 5. So the condition that would not be met would be the variance condition or the equal standard deviation condition. It may also be worded like that. The answer would be E. For 36, a researcher conducted a t-test of the hypotheses HO, where the true mean is 38, versus HA, the alternative hypothesis, where the mean is not 38. The sample mean was 35, and the p-value for the test is 0.0627. what would the p-value have been if the researcher had used the alternative hypothesis being less than 38 as the alternative hypothesis? So let's make sure this was actually not that difficult. It's actually pretty simple. You just have to remember what we're talking about when we have a two-sided test or not equal versus a one-sided test or less than or greater than. When it's not equal to, we're basically going to look at the probabilities on both sides. And these two added together would be our p-value. So this plus that would be 0.0627. So that means each one would be half of this, or about 0.3, I would say about 0.3135. This is for two-sided tests or a not equal test. Two-sided. But if we want to look at what the p-value would be if you just have a one-sided test, or just let's just say one of these, it would just be half of that. Half of this gives you that. They're equal on both sides. So our answer would just be that. It would be E, half of 0.0627. That's all there is to it. All right, 37. High school students from track teams in the state participated in a training program to improve running times. Before the training, the mean running time for the students to run a mile was 402 seconds with standard deviation 40 seconds. And after completing the program, the mean running time for the students to run a mile was 368 seconds with standard deviation 30 seconds. Let X represent the running time of a randomly selected student before training, and let Y represent the running time of the same student after training. Same student. Which of the following is true about the distribution of X minus Y? Okay, so let's write some statistics down. The mean of X, then be 402. Standard deviation of X, told is 40. So, 1 is 368. The standard deviation is 30. We're studying the distribution of X minus Y. So the mean of X minus Y would be equal to the mean of X minus the mean of Y, or 402 minus 368, which would be 34. Now, if X and Y weren't independent, the standard deviation or the variance of X minus Y would be equal to, that's actually, I don't even waste your time with this. Save some time. Variance or standard deviation of a difference can't be determined when you have variables that could be related, meaning are associated, because in this case, since each individual was compared to their own time, the amount of improvement we can argue that is based on the individual. Like probably those that were already those that were in really good shape to begin with probably didn't improve as much versus those who maybe never ran. So the mean would work, but the standard deviation or the variance can't be calculated because they X and Y are not independent. So what would work? So variables X and Y are not independent, and the mean is okay, 34, but a standard deviation cannot be given with the information. Yeah, so it would be D. All right. 38. A polling organization organized surveyed 2002 randomly selected adults who are not scientists and 2,748 randomly selected adults who are scientists. Each adult was asked the question, do you think that genetically modified foods are safe to eat? Of those who are not scientists, 37% said yes, and those who are scientists, 88% responded yes. Which of the following is a standard error used to construct a composite rule for the difference between portions of all adults who are not scientists and all adults who are scientists? Okay, so we're looking for the difference in proportions. Let's just say P, P1 minus P2 hats. Looking at that. So we just have to make sure we look at the correct equation in our formula packet, and we look at dealing with proportions. And what do you know? We got standard errors all in this column, and we got two population differences of sample proportions here, and these are basically the same except we're talking about sample in this case. So we just are going to use one of these formulas, this guy right here. So square roots of, let's say, one group is N1, let's make N1 2002, and N2 3,748. Plug that in. 2002 plus over 3,748. And from the 2002 group, or the group of the 2002 individuals, not scientists, 37% of them said yes. So for this group, you would have the P1 hat, so this guy, 0.37. And then 1 minus P hat will just be 0.73. Another group, 88%, their P hats, 0.88. Times 1 minus P hat, 1 minus 0.88, so 0.12. So again, just this formula. This is really simple. So we just look to see which one matches up. And it's the first one. It'll be A. Don't overthink this one. Literally, that's all there is to it. Oh, and I put 0.63. Whoa. My bad. 0.63. Luckily, there wasn't a 0.73, so I want to be caught off with that one. All right, 39. A polling agency conducted a survey about social media in which each person in random samples of 1,000 men and 1,000 women was asked what factor he or she considers to be the most important in deciding whether to connect on social media with another person. Responses are shown in the table. Okay. Well, these are all of our observed counts. Statistics. These are our observed counts. And we want to look what is the contribution to the chi-square statistic for men who selected business networking as the most important factor. So we're studying this group, men, business networking. And then if you remember, the chi-square statistic is equal to the sum of remember that. Let me just back. Let me just go to the formula sheet. So it's given to you. It's given to you. Don't worry about having to memorize these and forgetting. Chi-square statistics: the sum of the observed minus expected squared differences over the expected values. Observed minus expected squared over the expected. So we could brute force this and figure out each one. But luckily, in your calculator, you have a function where you can run this. And you want to go to the chi-square test, but first, you're going to go to a matrix. You're going to enter these values in a matrix. It's a matrix. In this calculator, it's over here. And you want to make a matrix with 2 rows and 2 columns. So I already did this one, but if it's not there, just change it to 2 by 5 and just enter these values in the matrix like that. These are your observed values. Enter them just exactly like you see. Once you do that, go to your stat and tests and run a chi-square test. There we go. The observed values are what we entered in matrix A. Expected to be any other matrix. I just put B because it's simplest. Calculates. This would be the p-value and the chi-square statistic from inference test. But let's look at what the expected counts are. So let's go back to matrix. And let's look at matrix B. Oops. And see in matrix B, I have the observed the expected counts. I'm going to look for what the expected counts were in this column, and you can see it's going to be 30. The expected was 30. So I just want to calculate this value for this observed and expected counts. So I'm going to do 45 minus 30 squared over 30. 15 squared over 30. 225 over 30. It's 7.5. That's your simple C. All right. Final one. Oh, this one's easy. Oh yeah, it's easy. Almost it's easy. It's a nice way to end. You can end this as confidently. Okay, so here we got a national survey asked 1,501 randomly selected employed adults how many hours they worked per week. Based on the collected data, 95% confidence interval for the mean number of hours worked per week for all employed adults was given as 41.18 to 42.63. Which of the following statements is the correct interpretation of the interval? Okay, so let's go through that. A, 95% of all employed adults work between 40. No, hopefully you don't mix that one up. The 95% confident, 95% refers to the strength of the interval, not the actual percent of the answer. The answer. The answer could be 17%. That has nothing to do with that. B, the probability is no, I already know right away. It's not a probability. Because it's a strength. Let me actually touch more on this. Especially when you're talking the probability of a sample. You already know what the sample produced. You're not going to be guessing about the sample. You're going to be using the sample to make estimates about the population. So it's never going to be like, oh, we're pretty sure that this interval contains a sample. So it's like, be careful of those ones. Those are not ever incorrect. C, of all samples of size 1601 taken from the population, 95% of the samples will have a mean between 41.18% and 41.18 hours and 42.63 hours. Okay, so this is kind of that, but this is actually referring to not the confidence interval, but the confidence level. Let me actually mention that. This is probably the most confusing one. Confidence level. If we said confidence level, that's what this would work. But that's a good one. That's a good way to test it. D, we're 95% confident that the mean number of hours worked per week for all employed So, see, again, in the sample, we know what the sample is. We're 100% certain of what the sample proportion is because that's how we got our data. That's how we create our confidence interval. So not D. And by process of elimination, it's going to be E, but let's just read it through. We are 95% confident that the mean number of hours worked per week for all employed adults is between 41.18 hours and 42.63 hours. That sounds good, and it's good. All right. There we go. Multiple choice section done. Congrats. Good luck. I hope that helps. And take a break and then move on to free response. See you later.